So in this lecture we're going to define rational functions and define some terminology associated with them. Well, a rational function is simply a function that can be represented as a ratio of polynomials. And we're particularly interested in rational functions of the Laplace variable s. So an example could be s over s squared plus 2s plus 2. That's a ratio of a linear polynomial and a quadratic polynomial. And the rational functions, you can think of them as being kind of a generalization, if you like, of the rational numbers. So as with rational numbers, we can cancel out any common factors. So in other words, this means that s times s plus 3 over s squared plus 2s plus 2 times s plus 3 is equivalent to, I'll squeeze it in here, the function that we just saw, s squared over 2s, s times s over s squared plus 2s plus 2. Just as 2 over 4 is equivalent to 1 over 2 in the rational numbers. These are the same rational function. These are considered to be one and the same rational function. And in fact, I don't know when you first were introduced to rational numbers, but you may have been told that what they do is take the integers and extend the integers to the kind of algebraic structure that we call a field. And in the same way, the rational functions extend the polynomials to a field, in particular by ensuring that every element has a multiplicative inverse. So for every polynomial p of s, 1 over p of s is a rational function. So by going from the polynomials in s to the rational functions of s, you give every element of the polynomials a multiplicative inverse, and that makes the set of polynomials, that extends the set of polynomials into what we call a field. So algebraically you can think of it that way. So as you've no doubt noticed, most of the transforms that we've seen so far are rational functions. In fact, more generally, they are either rational functions or rational functions multiplied by exponentials in S. So all of the transforms, in fact, that we've seen so far are rational functions, in some cases multiplied by exponentials in S. Now, when we have such a rational function, we're often interested in the roots of the numerator and denominator polynomials. The roots of the numerator polynomial are called the zeros of the rational function. Just as they're the points at which the numerator polynomial is equal to 0, so they are points where the rational function itself is equal to 0. So these are called the rational functions zeros, or more precisely, finite zeros. It's finite zeros. Similarly, the roots of the denominator polynomial, the points where the denominator polynomial goes to 0, are called the poles of the rational function. And to be perfectly accurate, you really have to call them the finite poles. So that's the definition of what we call the zeros and poles. If we go back to our example, therefore, because the numerator s is a linear polynomial, it has only one 0. Therefore, the rational function has one finite 0. And it's at s equals 0. And it has two poles. And they are at s equals -1 plus or minus j. They're complex poles. I should say two finite poles. We sometimes talk about poles and zeros at infinity in addition to these finite poles. And this is an example of a function that is said to have a 0 at infinity. Because according to the usual way we talk about taking limits of functions of a complex variable s as s goes to infinity, if we took such a limit for this function f of s, we would get 0, because the degree of the numerator is strictly less than the degree of the denominator. So under the standard definition used in complex analysis of the limit of f of s as s goes to infinity, that limit in this case is equal to 0. So this rational function is said to have a 0 at infinity. And in fact, it's reciprocal if you make the denominator into the numerator and the numerator into the denominator. By the same token, its reciprocal has a pole at infinity. But we won't have to worry about zeros and poles at infinity. So if we don't specify whether we're talking about finite or infinite poles or zeros, you should assume that we're talking about finite ones. There's a bit more we have to say. Most of the rational functions that we've seen so far when computing transforms are so-called proper rational functions. In fact, unilateral Laplace transforms are proper rational functions. And in fact, a rational function is said to be proper if the degree of its numerator is no greater than the degree of its denominator. So in other words, if it has no more finite zeros than it has finite poles. And if the degree of the numerator is strictly less than that of the denominator, then we say that the rational function is strictly proper. So if we can change this less than or equal to strictly less than, then we say that the rational function is strictly proper. So looking at our example again, we had s over s squared plus 2s plus 2. The degree of the numerator is certainly no greater than that of the denominator. In fact, it's strictly less than. So this function is not only proper, it is in fact strictly proper. And strictly proper functions, we were just talking about zeros at infinity, so strictly proper functions have zeros at infinity. But again, we're going to be concerned entirely with zeros and poles, with finite zeros and poles. So as I point out in the notes, a good exercise is to come up with a proof of the initial value theorem for the case where f is proper, f is rational, a proper rational function. It's just a good exercise. Now it turns out that if f of s is a proper rational function in the same case, then we can prove another final property of the Laplace transform, which we call the final value theorem. And that's even more useful than the initial value theorem. And that will be the topic of the next video. So I'll see you in that video.